points of the form a plus I times delta x. I starts at 0 and goes up to n, where n is that integer that I picked to make this true. That is a partition of the interval from a to b, where the delta x's are all the same, and they're all less than the given delta, which was chosen by uniform continuity. Here's the part where it's a sketch of the proof. So far, it's an actual proof. What I'm about to write is not completely rigorous. What can you say about this sum? That is the sum of the products of the oscillation values over each subinterval with delta x.
So for the partition, you have it starting at 0, but then for the sum, you have it starting at 1 for I.
Yeah, there are n subintervals. There are n plus 1 points.
Okay.
You know, for example, if n is 4, the 5 points are x0, x1,
Yeah, okay.
x2, x3, x4. Yep, but the summation will only have 4 terms in it. Here's the part that's not a full rigorous proof. That oscillation over each interval is going to be less than I'm forgetting epsilon over b minus a. Let's see. Although I think that what that means actually is I didn't quite choose my delta correctly. I actually want to do this, which I can do. A is less than b. Epsilon's a given arbitrary positive number. Epsilon over b minus a will be positive still. I meant to do that, so I made a mistake earlier. It wasn't technically a mistake in terms of logic. It was a mistake in terms of trying to get a nice epsilon at the end. Because this now, without proof, I'm going to claim is less than epsilon over b minus a, which is a constant. And that sum equals b minus a. So this equals epsilon. Why is this a sketch and not a fully rigorous proof? Proving this is less than epsilon over b minus a does take a little work because of the fact that the oscillation is defined in terms of a sup and an inf. It's not really a difference of function values. You may not attain the sup and the inf. So it takes a little bit of work to show this is less than epsilon over b minus a by this fact here. Definitely these points, the points in the interval, are within delta of each other because of how you chose that delta x. So this is almost a full proof. But because of that, I'm calling it a sketch.
In the P,
Uh-huh.
a plus I times delta x?
Yep, a plus I times delta x. Turns out monotone functions are also Riemann integrable, even if they're not continuous. As long as they're monotone, they're going up, maybe staying constant for a while, monotone increasing, they can have a jump discontinuity. No vertical asymptotes. We are talking about monotone functions over closed intervals, not open intervals. All monotone functions on closed intervals are also Riemann integrable. And there are other functions that are neither continuous nor monotone that are Riemann integrable. For example, piecewise constant functions, even with more than 2 pieces, say with a finite number of pieces to them, something like that, over some interval, neither continuous nor monotone, but definitely Riemann integrable. So these conditions are only sufficient conditions for Riemann integrability. They're not necessary. It's sufficient for the function to be continuous. It's sufficient for the function to be monotone. In either case, you get a Riemann integrable function. But you should know that there are Riemann integrable functions that are neither continuous nor monotone. But if a function is going to be not Riemann integrable, if it's going to have a chance, it can't be continuous and it can't be monotone. And the one that we had on the board over here earlier was one example. Of many. It's just the simplest example. All right, let's spend our remaining 10-15 minutes here talking about the Fundamental Theorem of Calculus. Why is this not closed? Don't save. Fundamental Theorem of Calculus. I'd like to actually just write down the equations in the theorem without writing out the theorems completely for today. It is typically a theorem I have you state on exam 3, and it is typically kind of a long theorem to state. If you look in the book, it's kind of a long thing to write down completely. But you can abbreviate, and you can write it down within a minute for sure. Okay? But I want to just look at the two main equations that come out of this theorem. One essentially says, if you differentiate an integral, where the upper limit of the integral there is the variable for this function, so I'm differentiating with respect to that upper limit of integration. As long as f is continuous, for example, this derivative can be found and it equals f of x. As long as little f is continuous, this integral as a function of the upper limit of integration, a weird idea, is a differentiable function of that variable up there, and its derivative is the function you're integrating at that value of x. The other equation is the one you're more used to. If you want to integrate from a to b, if you can find an antiderivative, capital F, you just do this. That's the one you're more used to. It's easier to understand. Calculate an integral by finding the antiderivative. You've probably done that, dare I say, thousands of times so far in your life. Maybe. For sure, hundreds of times. You've used this fact. Calc 1, Calc 2, problem stats. Where else do you use it? Multivariable calculus. So a little bit of differential equations. Okay, anything else?
Complex.
Complex analysis, we'll do some integrals to come. Yeah. There won't be this kind of integral, though. You end up doing this kind of calculation anyway sometimes. There'll be integrals of complex valued functions. This one is harder for people to understand. We do talk about it. It is in our calculus book. Sometimes it's called the second fundamental theorem of calculus. I prefer calling it the Antiderivative Construction Theorem version of the Fundamental Theorem of Calculus. It's a lot to say. What you're saying is, given a little f, I can construct an antiderivative. A function of x, whose derivative is the given function. That may not seem useful, but it actually is very useful to know. It does justify, for example, the creations of new kinds of functions, They're called special functions that you never learn about in pre-calculus and calculus, which are often useful. For example, the CDF, cumulative distribution function of the normal distribution, turns out to be what they call a special function. It's a new kind of function you've never heard of before, or maybe I told you about it. You know, the formula for a normal distribution involves pi in it and some square roots. What if we're just going to integrate something simpler? E to the negative x squared, like that. That has a graph that is bell-shaped. It's technically not a normal distribution because the integral of this from negative infinity to infinity is not 1. But I don't want to put all that other stuff in there. I just want to find an antiderivative of this. If you spent your entire life trying to find an antiderivative of this in ordinary kind of way, you would never succeed. There are unordinary kinds of ways of doing it. 2 ways, actually. One way is to use infinite series, Taylor series, to write it as an infinite series. And the other way is just to give it a name, to kind of cheat. What's its name? ERF. Square root of pi over 2 ERF of x is the answer. ERF. Stands for error function. It's related to errors in experiments, which are related to normal curves, right? Errors in experiments are typically normally distributed. That's why it's called ERF. It's an honest-to-goodness function. You know, the functions you learn about in pre-calculus, polynomials, rational functions, algebraic functions, exponential functions, logarithms, what else? Trig functions, inverse trig functions, and all sums, differences, products, quotients, and compositions of all those things, finitely many terms, or finitely many compositions. That's not all the functions there are. Right? You already know piecewise functions are another class, but you know, you learn about piecewise functions in pre-calc. What about other kinds of functions? Here's a new kind of function. It's called a special function. And there's infinitely many special functions. They don't all have names because there haven't been an infinite number of people to name all the infinitely many special functions. In fact, you could even create your own own special function and give it your name. I call it Kinney of x. You know, maybe my special function. Actually, let's do this. This is fun. Okay. I'm going to go ahead and call it Kinney of x. I'm creating my very own function right now, putting my trademark on it, my copyright on it. I suppose I could even patent it, but you do know you have to pay money to get a patent. Not that I want to pay money. If anybody used Kinney of x, then maybe they could pay me money, though. It would have to be useful. I'm going to create Kinney of x by integrating. What am I going to integrate? Well, something strange. I don't know, sine t cubed plus e to the t times cosine t as t goes from 0 to x. That's going to be Kinney of x. It's going to be an integral like that over there. The little f is going to be the sine of t cubed plus e to the t times cosine of t. I can graph Kinney of x. Plot. Well, let's graph not only Kinney of x, but this function, its derivative, except let's use x. I don't know, 0 to 2. We'll make Kinney of x be blue and its derivative be red. Takes a little while because it's doing a lot of numerical integrations to calculate it, but there it is. Kinney of x in red. Let's go further. That's, well, that's going to oscillate a lot. Ugh. I probably shouldn't go so hard. Abort, abort. Let's try 4. Because I have e to the x from there, it's probably going to start oscillating wildly. Maybe that's even too much. Oh, there we go.
Wow.
The red graph is Kinney of x. The blue graph is its derivative, which is even more interesting. It's the derivative of Kinney of x. That's an interesting thing. Okay. It is the derivative of Kinney of x, right? For example, Kinney of x has a 0 derivative right there. The blue graph has a 0. The slope of Kinney of x is positive right there. The blue graph is positive. The slope of Kinney of x is negative. The blue graph is negative. I have created my very own function. It's probably not very useful. And I suppose I could patent it. Okay? And the graph demonstrates this fact. Let me end class by doing one more other thing that's kind of cool. And then we'll get into more important applications and proofs next time. Suppose you wanted to find an antiderivative of square root of 1 minus x squared. You want to do that indefinite integral, and you did not have Mathematica available. And you ask your friend, and they say, well, just do a trig substitution. Let x equal sine theta. You remember trig substitutions? Kind of hard. It's just not super hard in this case. It can be done, definitely. But say you just were scared off by trig substitutions. And you're like, I don't want to do a trig substitution. I want to do this integral without it. Well, actually, this is an example you can do without a typical kind of method. Because you can think of it in terms of areas, and you can use this fact. The graph of square root of 1 minus x squared is the upper half of the unit circle. Consider the area under this curve from 0 to x. Symbolically, that area is going to be the integral from 0 to x of this function. Use some letter besides x for the variable of integration like t. That area will equal this integral. And in fact, by this fact that I circled here, this integral should be an antiderivative of square root of 1 minus x squared. Because its derivative, according to this equation, should be the integrand when you plug in x. It should be square root of 1 minus x squared. And this actually is not too hard to do. Just taking this area and breaking it up like this into a triangle and a sector of a circle. The base of the triangle is x. The height of the triangle is square root of 1 minus x squared. So the area of the triangle is 1/2 x times square root of 1 minus x squared. That's part of your antiderivative. What about the area of the sector of the circle? If you call the angle here theta, there's a theta in there, right over here. Turns out the area of a sector of a circle when theta is in radians is 1/2 theta times the radius squared. Now the radius is 1, so the answer there is just 1/2 theta. This should make sense if you imagine theta is 2 pi. Then the area would be pi. And in general, since the area is 1/2 theta r squared, when theta is in radians, if you use theta equals 2 pi for an arbitrary circle, you get an area of pi r squared when theta is 2 pi. But r is 1 here. That area is 1/2 theta. But you better get theta in terms of x. How can that be done? Geometry. Two parallel lines and another line crossing both parallel lines. You guys are in geometry right now. This is Euclidean geometry, not non-Euclidean. Alternate interior angles are congruent. That's theta as well. Inside that right triangle, trigonometry. So that's theta there. Its opposite side is x. Its hypotenuse is 1. So katoa. So sine. Sine is opposite over hypotenuse. Sine of theta is x over 1. Sine of theta is x. Theta is arcsine of x. There's your general, well, okay, the c is 0 for this integral, but for your antiderivative, you'd add on a plus c. Did it work? Is this really right? Well, if you have Mathematica take the derivative and don't simplify it, it doesn't look right. But I think if we simplify, it comes out right, I think. No, it didn't. Where's my mistake? Oh, arcsine. Yeah, what am I doing? Arcsine x. Okay, we want some suspense again. It doesn't look right when we don't simplify. But if we do simplify, yes, there we go.
Yes.
Come on. Okay, so you can do it without a trig substitution, but you still need to use some trigonometry and some geometry and the fundamental theorem of calculus in the form of the antiderivative construction theorem to realize that this works in the first place. All right, have a great weekend.